Now we still have a couple of minutes, so you guys can relax and enjoy. 2 minutes. Okay, that's working. It's also working. That's good. Mail. Okay. Okay, I think we can get started. It's time. So we're going to continue our exploration of instruction set architectures today. You can hear me? Say it again. Louder, louder. Like microphone. Is this better? Audio, is this better? Okay, everybody's okay in the back? No echo? Okay, if something is wrong, let me know. Thanks, Joel. So we're going to continue our exploration of ISA and its implementation, microarchitecture. I intend to wrap up ISA. Remember, we were discussing not just instruction set architecture, but also the implementation of the instructions on a given microarchitecture. I intend to wrap that up in 9A, and then in 9B, we're going to start with really microarchitecture fundamentals. And we're going to discuss some fundamental principles, and then we're going to build a microarchitecture from the ground up. Actually, we're going to build 2 microarchitectures from the ground up, single cycle and multi-cycle. But we'll talk about that later on when we get to it. And then we're going to pipeline them next week. So this is where we are. We're talking about instruction set architecture, the hardware-software interface, and also how it's implemented underneath, which is microarchitecture. We're going to see that distinction even more today. And these are readings, you've been exposed to this, and hopefully by now, you're very, very familiar with what's going on in this simple microarchitecture, LC3. We're going to see more of that also. And remember that we were discussing 3 major types of instructions: operate instructions, data movement instructions, and control flow instructions. And we actually went to a lot of detail in operate instructions. Today, we're going to cover more data movement and control flow instructions. But just to jog your memory, we've been talking about the instruction processing cycle, which looks like this. Every instruction goes through these 6 stages. And after the last stage, a new instruction gets fetched. And that's the sequential processing paradigm of the von Neumann model. We're going to deconstruct that at the end of today's 9A lecture, let's say. And we've also seen the control of the instruction cycle using this finite state machine, if you recall. I'm going to close this. Okay. And this finite state machine is what we have seen. Well, we've seen finite state machines in earlier lectures, but basically you can build a finite state machine to control that instruction processing cycle, right? You go from fetch, which is in this case 3 states, and then decode, and then basically change the control flow or execute the instruction in this particular case. But different instructions have different states after they're decoded. And we saw that the full finite state machine for LC3B, and you can find this also online on our website. Well, this is Spring 2022, but Spring 2023 has the same thing, basically. I hope. If you change that 2 to 3 at the end, you should be able to get the same thing. Okay, and remember that decoding is one particular stage in this instruction processing cycle, and it looks at the instruction registers top four bits in LC3 architecture, because those 4 bits indicate the opcode. And you can see that based on those 4 bits, the next state is different. And this is essentially how decoding is represented in the finite state machine. You go to a different state based on the opcode of the instruction. So it's beautiful, basically. Nothing is magic here, right? You can construct, given the specification of an instruction set architecture, what an instruction does, semantics of it, of every single instruction, you can construct a finite state machine that looks like this. And then you can construct the data path components and the control logic components that implement the finite state machine, as we will see. Now, we're not doing that. We're assuming that the finite state machine is given to us. The data path and logic is given to us. We're showing you initially how different instructions are implemented on the stuff that's already given to us. Somebody designed this, right? You can also verify it based on what you know. Okay, so we were talking about LC3 and MIPS instruction set architectures. These are 2 instruction set architectures we selected. They're very similar to each other, as I mentioned. We talked about instructions, opcodes. We talked about data types. If you remember, I showed you the binary coded decimal clock, and I showed you also a digital clock. And probably many of you were familiar with the digital data type of the digital clock, but binary coded decimal is a very different data type. If you remember that picture, I should have copied it over here, but how many of you remember that? Okay, good. Yeah. So that's essentially a very good demonstration of a data type, in my opinion. You yourselves as processors are familiar with the digital data type, and you're processing it well, but maybe not so much the binary coded decimal data type. Okay. Addressing modes, we're going to talk more about this today. This is how you actually calculate the address to figure out where your operands are. And this is one slide that we covered last time. Basically, it specifies where the operand is located and how you find that operand. We're going to look at this more today. And we also discussed many trade-offs in ISA design. We're going to also get back to this a little bit more today in lecture 9A. We especially talked about instruction types and addressing mode types and also data types over there and the complexity of them. We're going to see that again. Basically, you can choose your instruction set architecture to have complex instructions, complex data types, and complex addressing mode types that makes your instruction set closer to the high-level language, which makes it easy for the compiler or the programmer to compile down from a high-level language into the instruction set architecture. Or you can choose everything to be very primitive, very simple, like NAND, let's say, NOR, AND, which makes it harder for the programmer or the compiler to take a high-level language and compile it down to these very primitive instructions, data types, and addressing modes. But there are many other things that ISA specified. We're going to actually end 9A, lecture 9A, with some more examples of this relatively quickly. Okay, this is where we were. Well, we actually talked about operate instructions. And we were going to talk about data movement instructions and addressing modes in a little bit more detail. So let's start with that. Any questions before we jump into this? Okay, so data movement instructions facilitate data movement from memory to registers in LC3 ISA, with one exception, as we will see later on, which is the LEA. But basically, the format of these instructions are very similar. The opcode is specified, of course, like every instruction in the top 4 bits. And then the next 3 bits are either the destination register or source register, depending on whether it's a load or store instruction. And there are address generation bits, which are bits 8 through 0. that specify how the address should be computed for the load or store instruction. And there are 4 ways to interpret these bits depending on the opcode. These are called addressing modes, as you know from earlier. And you've actually seen a lot of these modes. We've seen PC relative. We've seen base plus offset. We have not seen indirect and immediate. So we're going to look at that in a bit more detail. But I'm going to cover the PC relative and base plus offset also. In MIPS, actually, MIPS is a bit simpler in this particular case. MIPS addressing modes consist of only base plus offset, which we have seen, and immediate, which we will see later on for the load store instructions. So let's take a look at the PC relative addressing mode. As I said, we've seen this already. Load and store instructions do this. And you can see that the opcode is different for load and store. These 3 bits are interpreted as destination register in load and source register in store, because what load does is it loads a memory location. It loads the data in a memory location and puts it into a register. That's why that register is a destination. What store does the exact opposite, right? It takes the data in a source register and stores it, places it into a memory location specified by the address. So how is the address calculated? Basically, in this particular opcode, this is specified by the ISA again, instructions at architecture. Semantically, the ISA says what load does is it sets the destination register to the value of memory at address calculated as follows: PC plus sign extended 9-bit offset over there, as you can see, right? And PC is, there's a sign over here that says it's the incremented PC. So basically, that's a specification of the ISA, because you naturally increment the PC when you go to the next instruction. So the expectation of the ISA designer was that, oh, the microarchitect is going to increment the PC anyway, so let me just specify the instruction to be this way. And store does exactly the same thing, except opposite. Basically, it takes the source register value and puts it into the memory location, specified by the address computed exactly the same way. These have basically these 2 instructions, load and store, even though they have 2 different opcodes, they have the same addressing mode, as you can see. Okay, so let's take a look at how load gets executed. This is very similar to the format that I used. You can basically see the machine code of this particular load. So, and this is the part of the data path that's relevant to the execution of the load. Basically, the instruction register contains this machine code that corresponds to this assembly instruction. And what this load does is, you first do the address calculation. And if you remember, the address calculation is incremented PC plus sign extended 9-bit offset that comes for the instruction register, right? So simple. We've seen sign extension in the last lecture also. We basically replicate the top bit of the PC offset so that we can have a 16-bit value. Okay, in this case, you can see the 16-bit value, and we have an adder, specialized adder. This adder is it's called the address calculation adder. We will see it in the data path. And that address is calculated and then placed into the MAR. That's the first step, memory address register. And then memory is set to read so that the memory at some point returns the data value into the MDR. And once the data value is in the MDR, that data value is taken from there, put onto the bus, as we will see, as we have seen earlier, but as we will see also later again, and placed into the register file, into the destination register. And destination register is encoded using these bits. So these bits are used to address the register file, and then there needs to be a signal saying that you should write enable the register file. So there needs to be control signals that are set appropriately, as we have seen in the last lecture. But these are the parts of the data path that are relevant to the execution of the LD instruction. Makes sense, right? So if you think about it, these are the data path elements that we've seen, but you could construct this data path yourself also, right? Based on the specification of the load instruction that I showed you earlier, you know exactly what to have, right? A PC plus 1, or PC, incremented PC, let's say, and sign extend offset coming from the instruction register, and then you need the adder, and then you basically connect it to the MAR, and MAR is connected to memory, and memory is connected to MDR, and then MDR should be connected to the register file, and you need to have elements to make sure that the register file is appropriately updated with the destination register address coming from these bits of the instruction, and write enable signal generated to make sure that the destination register is written. Right? So now you can see, actually, you can easily construct the hardware components to execute an instruction if someone throws you an instruction and tells you what this instruction is supposed to do. Again, there's no magic. All of these hardware components we've seen so far, right? Okay, so that's load. So the one interesting thing with this particular addressing mode is, as you can see, the addressing mode is relative to the program counter. That's why it's called the PC relative addressing mode. And it's relative, and it's relative in the sense that it's limited to what this PC offset 9 can encode. And as you know, using two's complement integer numbers, a 9-bit value can encode integers from plus 255 to minus 256, which means that the location of the address of the memory that could be calculated using this addressing mode is limited to a distance of 255 after this load or store instruction and 256 before this load or store instruction. So you can see that load instruction is here, and the data that you can address is a little bit limited before that and a little bit limited after that. If you want to address some other memory location, you cannot use this addressing mode. For example, if the data is located, I don't know, 1,000 bytes away from where this instruction is located in memory, you cannot use this addressing mode. So that's the limitation of this addressing mode, because the address is specified using an immediate offset in the instruction. Makes sense, right? So this sort of addressing mode has limited value, as you can see, because in many modern programs, this just doesn't work very well, let's say. It's a lot of burden on the programmer to actually figure out where the instruction relative to the data. So this is a little bit outdated in a sense. There's these addressing modes. Some of these addressing modes are a little bit old, if you will. But there are use cases still. There are use cases, especially when you're manipulating instructions and data around the stack. But I'll let you think about that. So basically, this addressing mode is a limitation. It cannot address far away from the instruction. So how do you overcome that limitation? There are multiple ways of overcoming that limitation. One of them you have seen, which is base plus offset. I'm going to introduce something else, which is indirect, which builds on basically what we have done. So this is what we have. Now, instead of load or store, we have load indirect and store indirect. And these are the opcodes. And again, these 3 bits are the destination or source register, depending on whether it's a load or store. And we still have PC offset 9. Now, let's take a look at the semantics of the load indirect instruction. Now, you can see that there is an indirection happening, right? What this says is calculate the address, just like we did earlier, PC relative, PC plus sign extended PC offset 9. Go to the memory location, get that data value, treat that data value as an address, and go to the memory location with that address and get that data value. So there's an indirection happening, as you can see, right? So we do 2 memory accesses to actually get the actual data value. And there are 2 addresses that we're dealing with. The first address is PC plus sign extended offset. And the second address we use to address memory is the data value at that address. Okay, so this is, you can think of this as pointer chasing, right? You're really chasing pointers. The first address is the address of the pointer, and the second address is the data value at the location specified by that pointer. Does that make sense? Okay, so this enables a lot of things, of course. Of course, the store instruction is exactly the opposite. Basically, store and load are, in a sense, duals. They just do the opposite things. One moves the value from the memory to the register, and the other moves the value from the register to memory using exact same addressing modes. Okay, so let's take a look at how the data path for this is constructed. Basically, it's going to be very similar, except we're going to do multiple iterations on the memory side. So let's take a look at this. So we first calculate the address, PC, incremented PC plus sign extended 9-bit offset, just like we did in LD. And this is the instruction, as you can see. So that address is placed into the MAR. Memory read happens using that address, and the data value is placed into the MDR. But then that we supply that data value, we take it in the third step and put it into the MAR again. Does that make sense? You read the memory, data value comes to MDR, and then we take it from the MDR and put it back to MAR, because we're going to use the data value in the first address as the address of the second access specified by the indirect load instruction. And then we do another memory read using that address, and the data value comes to MDR. And then we take the value from MDR to the destination register, just like we did earlier with load. Does that make sense? So 2 memory accesses, indirection. Now you can address anything in memory, right? But you just need to put the pointer close to your instruction. And that's the distance, you know already what the distance should be. It could be at most 255 bits far away, later than the instruction, PC plus 255, plus 1, of course, right, plus 2, sorry. Or, and also 256 bytes earlier. Any questions? So this is an addressing mode that could be useful for pointer chasing. So if you're doing array accesses, for example, this actually is very useful. Okay, so another addressing mode that gives you a lot of addressing range, if you will, is base plus offset. And you've already seen this addressing mode with LDR and STR. You've studied these instructions, well, at least LDR. But you can see this looks different right now, right? We have an opcode, we have the destination or source register. These are the same as LD, LDI, ST, STI. But now the bottom 9 bits are interpreted differently because of the opcode. Basically, the semantics say that in LDR instruction, if the opcode is, let's say, 0110, the address is calculated as the value in the base register specified by these 3 bits, plus a sign extended 6-bit offset. And then you go to memory and get the data value and put it into the destination register. Again, you can address anywhere in memory in this case. In fact, this is even more flexible because you can put any address into the base register, right? So because you're loading the data value from the base register. And store is similar, as you can see. So let's take a look at LDR, at least in the data path. Basically, it looks like this. If you have this instruction, destination is R1, source is R2. You basically take the source register, which is the base register R2 over here, from the register file, add to it a sign extended 6-bit offset coming from the bottom 6 bits of the instruction here, basically. And the address, resulting address is placed into the MAR. So that's the address calculation, as you can see. And we've actually seen this before, if you remember. And then memory does a read. You need to enable the memory to read using the control signals, as we will see again later on. And then the memory puts the result into the memory data register, and that value in the data register, memory data register, gets put into the destination register specified by these 3 bits in the instruction, which happens to be R1 in this particular case. Okay. So again, based on, if I didn't give you this right-hand side, but I just gave you the semantics of this instruction, you could have relatively easily constructed what you need in the data path for this purpose, right? And this is not the only way of designing it, of course. For example, you could potentially get rid of MAR and MDR. We will see that when we talk about single cycle microarchitectures, because single cycle microarchitectures by definition cannot actually, single clock cycle microarchitectures by definition cannot have registers, cannot put data into the registers before they can operate them for the processing of an instruction. But I'm getting ahead of myself, so keep that in mind. So there are multiple ways of designing the microarchitecture for the same instruction. Okay, again here, the address of the operand can be anywhere in the memory. So this addressing mode is very flexible, base plus offset. And this is why MIPS uses it as one of the major addressing modes. So let's take a look at how this address calculation becomes more complex. So before, I didn't show you the complexity over here in the LC3 data path, but this is all for address calculation, actually. This is to support all of the different addressing modes. So there's a global bus where you need to put the address. So assuming that your instruction calculates an address, you need to put the address so that it gets sent to the MAR, right? So that's global bus is needed. And then we have a multiplexer, gate MAR mux. This is basically, if you calculate the address, you should put it onto the bus. So you enable this gating signal. And that is fed from this multiplexer. And you can see that there are 2 paths coming out of this. One is coming from this adder, and the other is coming from instruction register 0 extended, etc. Right? So there are multiple paths basically. So this is the adder. This is the address calculation adder, and it enables basically all different types of addressing modes. For example, PC plus some sign extended 9-bit offset. You can select this input of this mux, and then you can select this input of this other mux, so that you can enable PC plus sign extend offset, which is PC relative addressing. Or you can take, let's say, source register 1 out over here. You can select this input of this mux, that's base register, plus sign extended 6-bit offset coming from the instruction register, right? So there, similar to this, there are other addressing modes that we have not discussed yet that are semantically required by the ISA. And this machinery, this hardware machinery, enables the implementation of those addressing modes as specified by the ISA. That's why these 2 muxes look relatively complicated, right? There are different ways of calculating the address, basically, depending on what the instruction is. Does that make sense? So the takeaway is that based on the definition of the ISA instructions, you need to provide the hardware, which is the microarchitecture, to support the execution of those instructions, because you're bound to that contract, right? The contract says you should execute these instructions semantically as it's specified. So you need to have hardware to execute those instructions semantically as it is specified. Okay, you can see the sign extension logic over here, and we've seen the 9-bit offset as well as the 6-bit offset. They're going to get sign extended. We have not seen the 11-bit offset, but that's part of the ISA also. Okay, so let's take a look at base plus offset addressing mode in MIPS. Basically, it's essentially the same, I would say. We've already seen this actually. Load word and store word use base addressing mode or base plus addressing mode. So this is, for example, a store instruction. Since I've given a lot of examples from loads, let's take a look at a store. Basically, you're storing this variable to the element at index 2 of this array addressed by A. And this is one way of actually writing that assembly code. This assembly code specifies that assuming that the base address of A is at S0, you take base register, that's the base register basically. You take the value in the base register, add to it 8. Why 8? Because this is index 2, and each element, with the word size in MIPS is 4 bytes, right? 4 times 2 is 8, and MIPS is byte decimal. That's the reason. And we've seen this before also. Basically, this says that memory at base register S0 plus offset 8 should get the value of value of source register S3. And this is assuming that, again, the variable A is stored in S3. Okay, there's no magic here. And you can actually encode it like this. In this particular case, MIPS is 32-bit instructions, so you have actually a wider range of encoding the offset, which is actually 16-bit immediate over here. Oh, I don't know, something happened. Yeah, this is the 16-bit immediate over here. And so you can see that we actually set it to 8. So it's sign extended to 32 bits, very similar to what we did in LC3, where we sign extended the bottom 6 bits to 16 bits. The word size of the architectures are different. That's why this is 32 here and 16 in LC3. Okay, hopefully that makes sense. Okay, let's take a look at an example program in MIPS and LC3. I won't spend a lot of time on this, but this is a high-level code. It's doing loads, adds, subtraction, and addition, subtraction, and a store, as you can see. Assuming that MIPS registers contain the address of A and the value of B and the address of B as follows, you can actually write an assembly program that executes this. And this is what it looks like. You basically first load the value A into a temporary register using the base plus offset addressing mode. It's A0, so base is the address of the array, and then offset is 0 because it's the index is 0, as you can see. And then you do the addition of the A to B, which is an S2, and stored in another temporary register, general purpose. And then you do the subtraction, stored in another temporary register. It doesn't have to be actually T2, it could be T1 over here. And then you store that temporary register, which contains the result C, into the destination memory location using the base plus addressing mode again, right? So it's very simple. Now we just did some assembly programming. We're not going to cover a lot of assembly programming, but you're going to do that in your labs. And I will mention that at the end of this lecture also. But it's relatively simple, as you can see, right? You just translate what is done in the high-level code to assembly. And normally assemblers or compilers can do this, translators can do this relatively easily. Of course, if you want to get a highly optimized code, it requires a little bit more work, as we will see later in microarchitecture lectures. So LC3 assembly, I will not go through this, but you can see it's essentially the same. Your load word is very similar to load register. Add is essentially the same as add. Add immediate is implemented using add over here. Basically, you subtract using a negative immediate value in both architectures. And store word is essentially store register over here. And the rest is basically different names for different registers, because LC3 ISA specifies registers as R0, R1, R0 through R7, as opposed to MIPS mnemonics. Does this make sense? Okay, so you can see here how the two architectures are very similar. Okay, let's also talk about immediate addressing mode. This is a little bit different. This enables you to actually construct addresses in a register or construct values in a register. So you want to store some address or store some value in a register. How do you do it? Using the immediate addressing mode, basically. It's called load effective address. It could have been called load immediate or load something immediate, as we will see in MIPS soon. But basically, the instruction looks like this. There's an opcode, there's a destination register, and there's a 9-bit offset. Because of the 9-bit offset, because of this opcode, we interpret it differently. basically destination register gets directly this value. There's no memory access here. You get PC plus sign extended 9-bit offset. So now you can actually load an address relative to the current instruction into a destination register, right? Directly. There's no memory access over here, right? We're just manipulating two registers, PC, well, one register plus some offset, which is immediate over here, right? So what's the difference from PC relative addressing mode? You don't access memory, basically. LEA does not access memory, whereas earlier load instructions that we have seen, they access memory. They're actually true loads, true data moment instructions. This is also a data moment instruction, except it doesn't access memory, right? It's basically constructing the data using the program counter and the bits in the instruction. Why this could be useful for manipulating the addresses, right? For example, you may want to decide some location to jump to later on based on the function calls you're doing. And it may be useful to load some address into your into a destination register that's relative to what you're doing. That's relative to the current instructions address. Okay, let's take a look at how this is actually executed. It's actually very, very simple. We don't need to do much. We already have the incremented PC plus sign extended 6-bit offset. That's our address adder to calculate the address. In this case, we don't need to access memory, as you can see. We basically take the address that we calculate using that adder, put it into the destination register. So the data path for the load effective address is very simple. Okay? Make sense? Okay. So basically, I've already talked about this actually. Let's take a look at where load effective address is over here. Can anybody find it? This is a test question. So basically, maybe I'll make it easier. You take the PC, so you select this input of this mux, and then you take the 9-bit sign extend offset, you select this input of this mux, you do the addition, and then the result goes into, through MAR mux, you need to gate MAR mux, and the result needs to go directly into the register file. So you need to have a data path for this. And you may say, okay, why are we taking the PC, not PC plus 1? Because the person who designed this data path assume that PC is incremented in an earlier clock cycle. So this data path is designed with a particular microarchitecture in mind. So you need to know what you're doing, basically, if you actually want to execute instructions semantically on this data path, right? So there's a path from PC, but there's no path from PC plus 1 into this MAR mux, because the assumption is that PC is incremented in an earlier cycle before you actually do the address calculation. Remember the instruction processing cycle? You fetch, you decode, you evaluate address, and we said that we increment the PC in the fetch stages. So when you go to the evaluate address, the data value inside the program counter register is PC plus 1. It's not the same PC that you started with when you were executing the instruction, when you started fetching the instruction. Okay? So all microarchitectures have basically, an ISA can be implemented in multiple different ways. This didn't have to be the way to implement it. You could have actually had another input coming from this PC plus 1 into this address mux. But that would actually increase the length of the clock cycle, as we will see later on. Okay. So let's take a look at a very similar instruction that exists in MIPS. Basically, LEA in LC3 is equivalent to LUI in MIPS. So this is called load upper immediate. And the idea here is the semantic specification is that it loads a 16-bit immediate into the upper half of a register and sets the lower half to 0. Let's take a look at how it does this. So basically, this instruction is used to assign 32-bit constants to a register. How do you actually populate registers? This is one way of doing it. So high-level code looks like this. A is equal to this blah, blah value, as you can see. This is the assembly instruction that constructs that value. You first set the upper 16 bits of the S0 register, to which variable A is assigned, to this value, 6D5E, using the LUI instruction, which we just specified. And then you OR that register with the bottom 16 bits that's specified by the high-level code. So the first instruction sets the top 16 bits of S0. The second instruction ORs the 32-bit value in S0 with a 16-bit value That's 0 extended, because this is not sign, there's no sign extension here. So that you actually construct the value SC, this value inside SCR using 2 instructions. Does that make sense? Why can you not do it using a single instruction? Anybody? Yes? Exactly, yes. Thank you. Basically, the instruction itself is 32 bits. You cannot specify a 32-bit immediate using a 32-bit instruction, and immediate values can be 16 bits at most in MIPS. Okay, so I'm not going to go through this, but if someone throws you, well, actually, if you cover this part, if someone throws you this machine code, you can completely reverse engineer and figure out the answer to the question at the top. What is the final value of R3? I should have covered this part also. But basically, if someone gives you this machine code with the addresses, etc., you could go to the ISA manual. This is a cheat sheet for in one thing, but of course, it doesn't specify exactly what the instructions do. But what you could do is you could reverse engineer what's going on, right? And this is a reverse engineered way of looking at it. So I'll let you study this on your own, basically, to make your life easier. You can decode it yourself. This is what the machine would do also. It's of course one instruction at a time, but you can see that based on by looking at the opcodes, you can decode the instructions, and instructions specify the addressing modes. LEA's addressing mode looks like this. These are the immediates, offsets, etc. And then these are the destination or source registers depending on the instruction. And then you can basically specify what the instruction is doing. And if you did everything right, you would get a final value of 5 in R3. So this is how people reverse engineer code, right? You can look at ones and zeros. Again, it's not magic, right? There's a decoding process that goes on. You can figure out everything that's going on just by looking at the ones and zeros in a machine. Make sense? Okay, so clearly we're not going to go through this. Otherwise, we would have the entire lecture maybe over here. Okay, so let's jump into control flow instructions. That's a nice thing to say, right? Jump into control flow, because control flow instructions all jump in the machine. Okay, so we've already seen a jump, unconditional jump. We're going to look at conditional branches today, or jumps. Basically, control flow instructions allow the program to execute out of sequence. You basically don't continue to the next sequential instruction. And there are 2 types, conditional branches and unconditional jumps. These are also called conditional jumps and unconditional branches. Branch and jump are essentially the same. Conditional branches are used to make decisions. For example, at a high-level language, if you have an if-else statement, how do you implement it? Basically, if tests a condition, and you execute one body of code based on that, if that condition is true, and you execute some other body of code if that condition is not true, right? So in assembly, you should really jump to a different place if the condition is true, and take the next sequential instruction if the condition is false, or vice versa, depending on how you actually implement the if and else logic, right? That makes sense, right? So you need an instruction to change the sequence of execution to be able to implement this decision-making logic that's demanded by high-level languages. And clearly, we need this in high-level languages so that we can actually make decisions in our programs, right? Okay, so there are multiple ways of doing this. In LC3, there's a way of doing this using condition code. So basically, there are instructions, conditional branches, that check the condition codes that are set by prior instructions. So you do some computation. That computation sets a condition code in the machine. And that condition code can have 3 different values, as we will see. And based on the value of that condition code, you can have a conditional branch that tests the particular condition codes and does a branching to one place or falls through in the code, as we will see. On the other hand, jumps, unconditional jumps, let's say, are used to implement loops and function calls. So if some condition is not true, maybe you go somewhere else, and you can have an unconditional jump that enables you to always loop, right? So at the end of a loop, for example, if you have a loop construct, you may have an unconditional jump that always takes you somewhere. And you can have a conditional branch that takes you out of the loop, right? Usually loops are implemented that way. You have a body of code. At the end, you have an unconditional branch to the beginning of the code, which basically keeps you iterating inside the loop multiple times. But then in the middle, there may be a testing logic that checks whether you should exit the loop. And that's a conditional branch that exits the loop to after the jump. Function calls are similar. Basically, if you want to call a function in one code, you should really use a jump instruction. In some ISAs, it's called a call instruction. In LC3, it happens to be essentially jump. And in MIPS also, it happens to be jump. But you may actually see call instructions also. This is function call instructions. And we've already seen these before, so I'm not going to cover these in a lot of detail. So let's take a look at conditional control flow. But we're going to get back to it actually when we talk about the single cycle architectures. So let's take a look at the conditional control flow, conditional branching. So I'm going to introduce the condition codes in LC3. This is one way of implementing branch instructions. And actually, LC3 does this. x86 ISA does this. PowerPC somewhat does this. So there are ISAs that do this. There are some other ISAs that don't use condition codes, which we may get exposed to later on when we talk about conditional branching in more detail. So every time an instruction writes a general purpose register in LC3, there are 3 single-bit registers specified by the ISA that are always updated. For example, if you add one value to another and you produce a result, since LC3 has one data type, which is 2's complement integers, the result can be either positive, negative, or 0. And those are our condition codes. These 3 condition codes are either set to 1 or cleared. So for example, if the written value is negative, if the result of the add instruction that's writing to a general purpose register is negative, the N condition code is set and Z and P are cleared. Obviously, this says that the value that was written by the last instruction was negative. If the value was 0, then Z is set and NP are cleared. And if the written value is positive, then P is set and NZ are cleared. Now we can test these condition codes, right? There are instructions that can test these condition codes to do the conditional branching. And again, x86 and Spark are examples of ISAs that use condition codes. And clearly, the x86 is one of the most popular ISAs. ARM does something different, but we will not get into it today. Okay, so let's take a look at how branch if 0 is implemented in LC3. Basically, branch if 0 means that branch take the change the program counter to a value that's calculated in a particular way as is specified by the ISA if the condition code set by the last prior instruction is 0, if the current condition code value is 0. So this is how it's specified. You can see the PC offset. You're familiar with it. Opcode is this, and there are 3 bits that you're supposed to test. Basically, which condition code is this branch testing? We're going to test 0, so this is going to be 1. So basically, NZP specify which condition code is tested, 1 bit each. Are you testing the negative condition code? Are you testing the 0? Are you testing the P? You could be testing different combinations. Basically, BRZ, as we will see, is going to test 0, but you could do BRNZ. If the value is negative or 0, right? You could do BRZP, which is a branch if the condition code is 0 or positive. Okay? Basically, NZP are the instruction bits to identify the condition codes to be tested. And ZP, the large ones, are the values of the corresponding condition codes in architectural registers. And these architectural registers are set based on the past instructions that have executed. The last instruction that have set it, actually, I should be more specific. The last instruction that executed to set it. TC offset is the immediate value, 9 bits, as we have seen. So this is the semantic specification of the instruction. Basically, this Boolean equation says that if we are testing the N condition code and the N condition code is set, or we are testing the P condition code and the P condition code is set, or we're testing the Z condition code and Z condition code is set, then PC should be set to something other than PC plus 1, which is this one. PC should be set to PC plus sign extended 9-bit offset. So the address calculation, as you can see, is PC relative. The addressing mode is very similar to PC relative load instruction, but it's a conditional setting of the program counter. Now you can see all the variations over here, right? Yeah. Does this make sense? So basically, you do a logical calculation. So let's take a look at how BRZ is executed specifically. So as I said, now we have a condition code. They're also called condition registers in different ISAs, N, Z, P. These are part of the architectural state. Remember, I showed the architectural state earlier. There's a general purpose register file. These are also a part of the architectural state. They are special purpose registers, 3 1-bit registers each. These are exposed to the programmer. It has to be specified in the instruction set architecture because there's an instruction, as you can see, that's manipulating them, right? Actually, all instructions are writing to them in LC3 because all instructions can set condition codes. well, maybe all is too much. Some instructions do not set condition codes. Every instruction that's writing to a destination register is actually setting the condition codes. I should be more specific. Okay, basically, let's take a look at how this is executed. Instruction register says branch, and we're testing the 0 condition code, 1. We're not testing the N and P, those are 0. But basically, this logic tells you whether the branch should be taken or not taken, whether the PC should be changed to the address that's calculated by PC plus offset 9 or not. And the logic is very simple, basically what I just described, right? If we're testing the N condition code and an N condition code is set, which is not the case here, as you can see. If we're testing the Z condition code and the Z condition code is set, which is the case here. If we're testing the P condition code and the P condition code is set, which is not the case. Basically, we're not testing P and N, so it doesn't matter what N and P are. We're testing Z, so it does matter what Z is, and Z happens to be 1, which means that the last instruction that wrote to a register wrote a 0 value. So we should really take the jump because this jump says branch if 0. And if that's the case, then the address that's calculated as follows, PC incremented PC plus sign extended offset, which comes here, and then there's a multiplexer over here actually, because there are different ways of branching, as we will also see. You should select that particular address coming out because of this particular instruction opcode, and that should go into the program counter. So that, again, there's no magic. The data path elements need to be constructed such that you have a path from this adder that calculates PC plus sign extended 9-bit offset coming from the instruction register, and ensure that you actually write that value into the program counter. Makes sense, right? Okay, so there are interesting things that you can play over here. What if NZP are all 1? Any question? Sorry, any takers? What would happen? You basically set these 3 bits, basically BR and ZP. You set all of these 3 bits in the instruction to 1. What is that? What does that instruction do? Thoughts? Basically, what this says is you're testing all of the 3 bits. If N is true, or if the N condition code is set, or if the Z condition code is set, or if the P condition code is set, take the branch, meaning change the control flow. Now we know what this is, right? This is an unconditional branch, because there's no time where N, Z, P, any of these, all of these condition codes can be 0. Otherwise, you have a bug in your program, right? The values that you have as 2's complement integers can be either negative, positive, or 0. There's no other option, right? So if you're actually testing all of the condition codes, you basically turn this unconditional branch, conditional branch into an unconditional branch, okay? Similarly, if you set NZP to all 0s, basically you're not testing anything in that particular case, right? So that's essentially a no-op instruction, no operation. I have not introduced that instruction, but if you're not testing any of the condition codes 0, 0, 0, if you set NZP bits to all 0s, that's a great exam question, by the way, but I've already given you the exam question. If you're not testing it, then the instruction is not doing anything, right? Because you're not testing any of the condition codes. So you're never changing the program counter to this value, which means that the program counter should naturally increment to the next value because just you fetch this instruction, which means that the instruction is essentially a no operation. Okay, so branches are fun, as you can see. Well, I guess I've already given you. I was not going to give you the answer, but fine. Okay, so let's take a look at how this is implemented in MIPS. MIPS actually has a little bit more complicated things. MIPS doesn't have condition codes. MIPS is an instruction-set architecture that doesn't use condition codes. It basically has branch instructions that are more powerful. Branch instruction can do some calculation on registers, and based on the value of the calculation, based on the result of the calculation, you can actually branch. You can change the program counter or not change the program counter. For example, one example is BEQ, branch if equal. It takes 2 source registers, no destination register. It's the semantics is that you compare the source registers, and if the source registers are equal, the program counter gets set to a value that's equal to program counter plus sign extend offset, as we will see. This is the immediate, as we have seen. This is used immediate addressing mode. Basically, the semantics looks like this. If the value in RS is equal to the value in RT, then PC gets PC plus sign extended offset and multiply by 4 because instructions are 4-byte elements, as you know, right? Because MIPS is byte addressable, as we've seen this also before. Does that make sense? Otherwise, if RS is not equal to RT, then you don't do anything. PC is incremented anyway, based on the model of execution. And there are variations in MIPS like branch equal, branch not equal, branch less than or equal to 0, branch greater than or equal to 0, that tests, that basically do different types of comparisons between RS and RT. Okay, so let's take a look at how these are implemented, how branch equal is implemented. If you want to compare two registers and basically take a branch based on whether or not they're equal to each other, this is how you do it in MIPS. It's one instruction. In LC3, it's more work. Basically, assuming that the register that you're comparing to are R1, let's see, and R4. No, R0, sorry. R0 and R1. This is what you do. First, you subtract R1 from R0. How do you do that? Basically, you take the 2's complement, or R1. You take the bitwise not of R1, and then add 1 to it. That's actually the negative value of R1. You basically constructed minus R1 into register R3 here, after not and add. And then you add R0 to it, which basically calculates R0 minus R1. And the result is written to R4. Now the result, if the result is 0, the 0 condition code is set after this add instruction. And this branch will be taken because it tests the 0 condition code. If the result is not 0, either the negative or positive condition code will be set, and this branch will not be taken. Right? So now you can see another example of the trade-off. We've seen this similarly earlier with the sub-I instruction, for example, in MIPS and LC3. But basically, the same functionality can be done in both ISAs, as you can see, because both of these ISAs are functionally complete. They're also Turing complete, but we're not going to get into that. But basically, it requires more instruction in LC3 because it doesn't have a powerful conditional branch instruction. Whereas MIPS has a powerful conditional branch instruction. But there's always a downside, right? Everything's a trade-off in what we do. Here, you have fewer instructions in MIPS, that's great, but more logic complexity. The instruction is more complex. It's not a simple instruction like what LC3 has, right? Now, in the same instruction, you need to do a subtraction, and also you need to do the address calculation, and you need to make a decision. You need to make a decision as to whether or not to set the program counter. Well, I think we've come to close to the end. Any questions? Okay, so now we've seen actually a lot of instructions. There's a lot more on ISAs. I'm going to take a break in a few minutes. I want to cover a couple of things. There's a lot more to cover on ISAs. Unfortunately, we don't have time. So when I actually gave these lectures at Carnegie Mellon, it was a different class, and we covered a lot of interesting trade-offs, but we don't have time. And many different ISAs have been around over decades. We're going to see some of these later on. And this is just a list over here, right? Actually, there are many, many simpler ISAs today. x86 is very complex. A lot of the ISAs that are up here are quite complex ISAs. And we're going to see VLIW, for example, later on. So the fundamental differences are actually what we have just discussed. How do you encode how do you specify the instructions? What do they do? What is their complexity? How close are they to the high-level language? How complex are they? How complex are the data types? How complex are the addressing modes? And I've given you this example earlier, right? This is the fundamental choice that you make as an ISA designer: complex instruction versus simple instruction. And we've already seen this, right? Advantages of complex instructions, complex data types, complex addressing modes. You get denser encoding. So your instruction working sets are much smaller. And you get a simpler compiler. On the other hand, you get disadvantage. You get larger chunks of work, which are harder to optimize. Compiler has a lot less opportunity to optimize, and you get more complex hardware. Now, again, performance, as I said earlier, performance is a different ballgame, right? If the which one is better performance? And the answer is I don't know. It really depends on the underlying implementation. You can actually have hardware that is great at executing complex instructions or simple instructions that is really a function of the microarchitecture that we're going to see. And we're going to see the performance equation soon, actually. These will directly affect the performance equation. So I will mention this when we look at the performance equation in the latter part of this lecture. So remember this picture. Always remember this picture, basically. You have a semantic gap, and how close you are to the ISA, how close you set the ISA to the high-level language makes the software job easier in this particular case. Hardware's job harder, or microarchitect's job. And here, it's exactly the opposite. So on the left side, you have a small semantic gap. You have less work for the software designer, more work for the hardware designer, and the optimization burden falls on the hardware over here. Whereas on this side, you have a large semantic gap and more work for the software designer, less work for the hardware designer. Optimization burden is on the software here. Now, let me actually introduce something, an injection that actually changes the trade-offs. You can actually translate from one ISA to another implementation ISA that could be invisible to the programmer. So this is what we're assuming is visible to the programmer, right? That's the hardware-software interface. It could be very complex. You can say, oh, I'm going to translate this to some other code internally. I'm not going to tell anyone about it. Use a software or hardware translator and have an implementation ISA with simple instructions, simple data types, and simple addressing modes. Most complex ISAs are implemented this way today, actually. To make the hardware design simpler, there is either a software or hardware translation mechanism that's not visible to the programmer. It's purely microarchitectural that does this translation. For example, x86-64 can get translated to ARM architecture, completely different ISA. And this is done. This is done on this machine. Well, I don't know about this machine, on this machine for sure. So you may have seen Rosetta, for example, the binary translator that Apple uses. They basically enable execution of x86 code, but they don't really have native hardware to execute x86. They basically use a software translator with some hardware support that they don't disclose how to make it fast. And some people claim that x86 code executing on this machine is much faster than some x86 code executing on x86 machines. I don't know if that's true, but it could be true. I mean, depending on how you design the system, right? Okay, so this exists basically. Intel AMD processors actually do a very similar thing, except they use a hardware translator. They take x86-64, they use a hardware translator and translate the instructions to secret micro-operations. And these secret micro-operations constitute an implementation instruction set architecture that is very simple, actually. Okay, and basically these machines, the x86 processors on these machines actually do that. Other folks also do similar things, like NVIDIA Denver is a processor that does using a hardware translator that takes the ARM ISA and translates it to secret micro-operations. And if you're interested, you can read about it. So they actually do very interesting things, which I will not talk about over here. Actually, their translator is software/hardware. I should really change the slide to software/hardware. I'm going to do that in the break. And then there are other systems that try to compete, for example, with x86. This is from 1990s, early 2000s. There was a company called Transmeta that tried to compete with Intel and AMD. And their goal was to actually design a very efficient software/hardware, hardware-software co-design translator that takes x86 instructions, x86 ISA, and translate it to a VLIW ISA, very long instruction work, that actually exploits parallelism in the code. And we will see VLIW ISAs later on. They did not succeed in terms of performance, but their systems were quite efficient, actually. Okay, there are a lot of other trade-offs in the ISA. I'm going to skip the slide because we don't have a lot of time, but you can read it. Clearly, number of registers is a trade-off also, right? How big your encodings for the registers are. If you have more registers, you get better register allocation. But now you have larger instruction size and larger register file size. Again, hardware-software trade-offs are quite interesting over here. Okay, so if you want to know more, you should either ask questions or go and study some of those lectures. But this is where we will stop and take a 10-minute break. Well, okay, almost on time. We'll be back at 21. And then we're going to continue with some more critical thinking and microarchitecture. Oh, I should change this. Okay. Okay, let's get started. So now we're going to talk a little bit more about ISAs and then talk about microarchitecture. But before I move on, I should say that this is a very powerful thing, and a very complex instruction set architecture like x86 today can be translated using a hardware or software translator to a very, let's say, relatively simple ISA that consists of more primitive instructions. And this hardware translator can be made efficient over decades. That's what the x86 processor market is like today, basically. That's why it's very difficult to break into that market designing on processors, because there's a lot of secret sauce that these companies have in terms of how to translate a complicated instruction set architecture efficiently using hardware and some software also into secret microoperations. This could be done through some microcode engine. This could be done through pure hardware combination logic, for example. And there's a variety of techniques that people have developed over decades to make this very efficient. Keep that in mind, basically. So what is difficult to change is that this, right, the hardware-software interface. This is the interface that gets exposed to the compiler, programmer, operating system. And over decades and decades and decades, people write software. It becomes very difficult to change it. I mean, you can add instructions, of course, but as we discussed last time, you cannot remove instructions. Once you start removing stuff, instructions, data types, addressing modes, you're really messing with the entire software ecosystem that built on that ISA, and you may actually lose a lot of customers if you do that. But there's a lot of flexibility that you have underneath the hardware-software interface. You can actually do a lot of stuff over here, and this is all microarchitecture at this point. That microarchitecture could use a hardware translator to translate the ISA into something, or software translator to translate the ISA into something. So basically, all of this part is microarchitecture. So keep that in mind. So microarchitecture is actually something a little bit more fluid than just hardware also. Okay, so it's good to think critically here. Okay. So this is where we stopped at some number of minutes ago. So let's go back. Let's revisit some concepts that we've discussed. So von Neumann model, we said it's been very successful, and these are the two hallmark concepts of the von Neumann model: stored program, sequential instruction processing. Right? And we've already discussed this. Basically, it has two key properties: stored program memory is unified between instruction and data. The interpretation of a stored value depends on the control signals. And we already answered the question: when is a value interpreted as an instruction versus data? It basically depends on when you refer to that value in the instruction processing cycle, right? Whether a value fetched from memory is interpreted as an instruction depends on when that value is fetched in the instruction processing cycle. If you fetch the value in the fetch stage of the instruction processing cycle, interpret that memory value as an instruction because the program counter points to it. If you get the value or fetch the value in the fetch operand stage of the instruction processing cycle while the instruction is being processed, you interpret the memory value as data because you formed an effective address as specified by the instruction that refers to the data. So this is how control and stored program concepts are coupled in the von Neumann model, basically. Stored program is enabled by the control of the instruction processing cycle. And depending on where the control of the instruction processing cycle is, determines whether you interpret the bits that you see, raw bits that you see as an instruction or data. So it's beautiful, as you can see. Now let's take a look at sequential instruction processing. We said that you have the abstraction that you provide to the program is one instruction is processed, fetched, executed, and completed at a time. And there's a program counter, it's advanced sequentially. So that's good. We're going to assume that. And these are the beautiful pictures that we have seen. Now I will ask, let's say, a critical thinking question. Is this the only way that a computer can process a program? Anybody has a better model, different model than von Neumann model? No? Okay, yes. That's true. Yeah, you can basically break the stored program. Exactly. So that's one way of separating that. Yes. Okay, there you go. Yeah, in some examples of in-memory computation can actually couple memory and program together. I agree. Yes, not all of them. Some of them are obeying the von Neumann model, but some of them actually change the model quite a bit. For example, if you do analog computation in memory parallel across many banks, it actually leads to a change in the von Neumann model. These are good, actually, very good. What else? Anybody? Maybe I want to break. Yes, go ahead. That's true. Yes. That's true. I mean, those break the von Neumann model, but I was also thinking of more general purpose paradigm, right? Once you go entirely specialized, of course, you can, you don't even need to have programs, right? Almost. But very good. I mean, these specialized chips like hard-coded application-specific integrated circuit that just do video decoding, for example, they don't really obey the von Neumann model, right? Systolic arrays that are at the core of a lot of machine learning accelerators, as we will see, they don't obey the von Neumann model. So we will see examples of it. So basically, the answer to this question is no, as you can see. But let's talk about the general purpose domain. In the general purpose domain, qualified answers, it's been the dominant way. Basically, this has affected all of our designs so far. It's been the dominant paradigm for computing, basically, for N decades. And it's still going on. It's being challenged right now with things like in-memory computation, for example, increasingly more specialization that's happening across the domain. So general purpose computing maybe is not as important today. I don't believe that fully, but certainly there's been a lot of specialization that has happened also. But now let's examine a completely different general purpose model. So I'm going to introduce a completely different general purpose model for processing computer programs. And it's going to be as powerful because, well, as powerful in the sense that you should be able to specify any program using this model. And it doesn't have the sequential instruction processing aspect of the von Neumann model. And that's the data flow execution model. How many people have heard about data flow execution model? Okay, no one? Okay, that's surprising. You didn't even cover this in high performance computing class? You didn't take that yet, I guess. Maybe you're taking it. Okay, fine. You're taking it at some point, fine. But maybe you don't cover that also, yeah. But this is very fundamental, right? So von Neumann model, an instruction is fetched and executed in control flow order, right? We've said that, as specified by the program counter or instruction pointer. Sounds nice. It's sequential unless explicit control flow instructions change the control flow. Whereas data flow model, it's somewhat analogously, you can define it this way. An instruction is fetched and executed in data flow order. Now, what does that mean? What is the data flow order? Control flow order, I can say, okay, I wrote the program semantically as one instruction, next instruction, unless the control flow changes. Data flow model says, basically, it depends on the data. If the data value of an instruction is available, you fetch and execute it. Sounds good, right? It makes a lot of sense in the sense that in von Neumann model, you fetch an instruction and then you wait for the data. Here, you don't do that. You basically say, I fetch the instruction whenever the data value is available. So I can execute many instructions whose data values are available, and an instruction is only fetched and it's executed when its data value is available. Right? So it seems like a more parallel model, fundamentally, right? And also, it may be less bottlenecked by the, let's say, waiting for data aspects that we're going to talk even more later on. So basically, data flow order means an instruction is fetched and executed when its operands are ready. In other words, we just got rid of the program counter. We just got rid of something so fundamental, something that has affected us for, let's say, so many decades, right? Since 1940s. Does that sound good? That's beautiful, right? So how does it work, basically? Instruction ordering is specified by data flow dependence implicitly, not explicitly. I mean, you could also do it explicitly, but as we will see some explicit specification, actually. I mean, ordering happens implicitly when the program is executing, basically. There's no specified ordering like in the von Neumann model. There's a specified ordering, right? But here, each instruction specifies which other instruction should receive the result. But it doesn't specify when the instruction is executed. The program doesn't specify when an instruction should be executed. So an instruction can fire whenever all of its operands are received, meaning they're ready, because somebody actually produced them. So you can think of instructions as producers of value. So an instruction, what does an instruction do? It produces value for some other instruction, right? In the end, the latest instructions that you care about produce the value for the user, right? Produce an output for the user, for example, right? Or maybe some other program. So basically, it's really all about the data. The goal of an instruction is to produce value for some other instruction. And the goal of an instruction is also consume the value produced by some other instruction. So now we're thinking of a producer-consumer model between instructions, as opposed to a single sequential execution model. So potentially, many instructions can execute at the same time. So basically, this is inherently more parallel. So let's take a look at an example between these two. So consider a von Neumann program. This is, I mean, at the higher level, this is a von Neumann program, right? You see A and B are the only inputs, and Z is the only output. Assuming you care about only A and B and Z, everything else is intermediate values that are communicated between instructions, right? So how do we specify it in a data flow? Data flow is fundamentally also a more graphical model of computation. Looks like this, basically. This is sequential, as you can see. So what is the significance of the program order? Program order actually enables you to think better, let's say. We're going to get back to that. What is the significance of the storage locations? I already said this, actually. Except for A plus B, A and B, and Z, everything else is intermediate values. Everything else is used to communicate data between instructions. For example, V over here, it's used over here. W over here, it's used over here. X over here, it's used over here. Y over here, it's used over here. And all we care about is the end result, Z. So in a sense, the storage locations are actually values that are to be communicated between instructions. So you can actually visualize this program as a data flow graph. There's a particular name for it. This is the data flow graph for this program. So you can see inputs A and B. And data flow graphs are basically have nodes and then arcs connecting to nodes. And this is the data flow specification of the program, right? You have A plus B over here. Its value is communicated to the left side of this instruction and the left side of this instruction. And then you have B times 2 over here. It's a special node, as you can see. But you could have had another input that's set to 2. And its values are communicated to these two instructions, which happen to be these two over here. And then you have the values that are generated by those two instructions communicated to the inputs of the last instruction. That's a multiply instruction over here. And the result is Z. So you see A, B plus Z. Only these need to be stored in registers, perhaps, right? Everything else can be communicated directly between instructions. So there could be temporary values. It could be interconnect, for example. So basically, you can specify your instructions this way. This is my instruction. And the result goes to this instruction, right? And you can see that there's no ordering between this instruction and this instruction. They could be executed both in parallel if you have the functional units to do so, or in any order. Except you need to obey the data dependencies, of course, right? When this instruction executes, it generates a result. This instruction can only execute after it receives the value from this instruction over here and this instruction. So fundamentally, the execution happens as instructions execute and generate their data values, and instructions fire when their input values are available. Make sense? So how do you make it happen? Well, I guess maybe before we go into it, which model is more natural to you as a programmer? Who says von Neumann? Okay, a lot of people probably. Who says data flow? Okay, some people say data flow. Why do you say data flow? Just to not to put you on the spot, but it looks nicer. I kind of agree, actually. It's more graphical, right? You can actually reason about the parallelism more easily. Yes, there's a question. Well, you could make it synchronous. Yes, you could design a synchronous machine to enable this, basically. The underlying implementation of this can be completely synchronous, yes. Okay, so maybe just to qualify my question earlier, imagine a world you were taught to do this when you were, let's say, born, not born, but whenever you learned about programming. Maybe this would be more natural to you, I don't know, right? So we don't know, actually. We don't know which one's actually a better programming model, but certainly because of the dominance of the von Neumann programming model, the sequential, I believe is more, let's say, familiar to many people. But if you once you get started in the data flow, you can actually do a lot of things. So basically, let's go a little bit more into depth over here. So this is actually how you can actually design application-specific integrated circuits as well as FPGAs, but this could also be a very general purpose model, as we will see. In fact, we're going to get back to the microarchitecture later on, a few lectures later, when we talk about out-of-order execution, we're going to talk about existing machines that take the sequential program and internally convert it into data flow graphs and execute them as data flow graphs. Why? Because sequential program, we want to extract parallelism out of that sequential program, and you can actually do that extraction by turning the sequential program internally, invisibly to the programmer, into a data flow graph. This is fascinating. All high-performance machines today do this. They take the sequential code that the programmer writes, convert it to a data flow graph. High-performance general purpose CPUs, I should say. GPUs do something else, as we will see also later on. Okay, that's why this is actually very important. But let's take a look at the data flow as exposed to the programmer. So basically, in a data flow machine, programmer writes data flow nodes. In fact, you could program it graphically, as we will see. A data flow node fires, it's fetched and executed when all of its inputs are ready. So there needs to be machinery to enable that. I'm not going to talk about exactly how the microarchitecture of a data flow machine is implemented. Later, we're going to see a glimpse of it when we talk about out-of-order execution. Basically, when all inputs have tokens in them. So let's take a look at a data flow node and its ISA representation. There's a multiply node. It has 2 inputs and 1 output. And you can see that this is the opcode. This is the first input. Is it ready? This is the second input. Is it ready? So there needs to be something to check whether it's ready. And then there's destination of the result. Which instruction in what memory location is going to get the result? And that could be specified as instruction at memory location 120, left node, meaning the left input of that instruction. And then there's a right input, of course, right, if it's a binary, if it has 2 inputs. Okay? So it's beautiful, basically. You can specify an instructions at architecture, just like we did earlier in the von Neumann model. And now, of course, what are the nodes? You need nodes to be able to construct programs, right? And these are the nodes. These are some example nodes. I will not go through all of them, but conditional nodes. How do you implement decision-making in this logic? So this is a branch node. Branch node has 3 inputs. 1 data input, X, 1 control input, this is over here, but it could be false or true. And what it does is, and then two potential outputs, true output and the false output. And if the control input is false, the data input, when it's available, so basically the instruction gets fetched and executed when both the data input is ready and the control input is ready. You have to have tokens on both sides. And that instruction, the semantics is that if the control input is false, the data input gets passed to the false output over here. Otherwise, if it's true, it gets passed into the true output. In this particular case, it's false, as you can see. So X gets passed to the false output, which is connected to some other instruction, and true output is presumably connected to some other instruction. So based on, now you can actually specify a program graphically. This is how you can implement if then else, for example, right? If some condition is true, and how is this false computed? It's computed by some other part of the data flow graph that basically computes the condition of the branch, if you think about it. Okay, is it still natural to you? Okay, good. So relational, this is how we can actually compute false or true, for example. So relational, this is a particular node, greater than node. If this fires, this gets fetched and executed when both of the operands are ready, both that have tokens. And it basically computes if the left input is greater than right input. In this case, it's true. So the output gets assigned a true token, if that's the case. Otherwise, it would have gotten assigned a false token. Now we can connect this to this one, right? So I can actually do graphical programming using this model. How many people know about barrier synchronization? Okay, not many. But this is a way of synchronizing between different threads. You will see it later on in your program. But basically, what this node says is you can actually implement very complicated instructions. That's the point over here. What is this instruction doing? This instruction says, wait until all of the input values are ready. Only after that, send the input values to the next stage to your outputs. What is this useful for? It's useful for synchronizing. You may have a huge data flow graph, and you need to wait until all of the input values to this barrier synchronization is ready. You may have many, many parts of the data flow graph computing many things, but you wait until all of them are ready, and then the next part of the data flow graph starts. So it's a beautiful construct, and you will see that when you program in parallel programming. Okay, so let's take a look at a fun program. This is not the perfect data flow graph, but it's used for, let's say, education, and you can start computing what this is. Basically, I have a question for you. Basically, n there are two inputs, as you can see. N is over here, and initially this value is 1 over here, and then there's one output over here. So n, assuming that n is a non-negative integer, what is the value of out over here? It's a relatively simple one, but basically, let's take a look at. While you're doing this, maybe trying to answer this, I will tell you what's happening over here. So you have a copy node. Copy node takes the input whenever the input is ready. In this particular case, we assume that the inputs are ready. 1 and n. Of course, n should not be specified as n. It should be maybe some number like 10. That's a real input, right? It copies the value 10 over here and over here, and then this node fires. It basically compares the input value to 0. If it's greater than 0, it basically produces a true thing over here. That makes sense, right? And then this node fires when this token is available, and basically copies that true or false input to over here. The control nodes, as you can see, these are the branch nodes, conditional nodes that we have seen earlier. So there's some controlling going on based on the value of n, right? If n is greater than 0, you basically take this value and pass it through the true path over here. So this node fires when this is available and when this is available. And then if this Boolean is true, it passes the value 1 over here. Well, at least in the first iteration, let's say. Otherwise, it's basically supplies the output. So you kind of have an idea that for the output to be generated, this bool has to be false, right? Otherwise, the output doesn't change, and the input gets passed over here, right? Now, what is that? What is happening over there? Let's say. So this n gets copied over here. So this kind of n, let's say 10, and the data flow, and this node fires when this value is available and when this value is available. So basically, you test. We've already done this, right? If n is greater than 0, this is true. So again, if n is greater than 0, if the value you're dealing with is greater than 0, you're passing the value over here, and you're passing 1 over here, or whatever comes in out of the next iteration over here. You see what's going on? Anybody figured out what this is? Yes. M factorial. Who agrees? Okay, a lot of people agree. Who doesn't agree? Don't be shy. Who has no clue? That's also okay, because you'll study. Okay, basically the answer is correct. It's M factorial here, if n is a non-negative integer. So basically, I've shown you what happened, right? You basically, if n is greater than 0, in the first iteration, 1 gets passed over here, and n gets passed over here actually, because n is copied here, and n is greater than 0. So this node fires. So this is n. N gets copied again. So you multiply 1 with n, and then you input that back into the input value basically over here. So that's the nice part. It's not that part is not done very well in this data flow graph, but basically this thing that's going back over here is the input to the data flow graph again. Okay. Yeah. So basically you have n over here, and you decrement the n also, right? So that's the next input. So this input is m minus 1, and this becomes n. Sorry. So this input to the copy node actually comes from the decrementer, and this input to this particular node that tests whether what you should take as output comes from the multiplier over here, multiply instruction. Basically, at the end of the first iteration, you have n over here and n minus 1 over here, and you do the same thing basically. At the end of the second iteration, this outputs n times n minus 1, which goes over here, and you decrement, this becomes n minus 2. And you keep doing this, you keep multiplying, and this keeps multiplying, n times n minus 1 times n minus 2, n minus 3, n minus 4, until n becomes equal to 0. And when n becomes equal to 0, this evaluates to false, and this evaluates to false, so your output becomes the n factorial that we've calculated, and this false value gets killed. I didn't define that, but this node says basically that false value gets killed, so the token gets killed, and the program doesn't have any token iterating over these instructions anymore. Does that make sense? So that's a way of implementing n factorial in data flow, assuming this sort of instruction set architecture. As I said, it's not perfectly displayed, but it makes the point. So as you can see, this is pretty powerful, and you can implement any program this way. In fact, a data flow is so powerful that you can actually, the entire world can be modeled as data flow. And it's good for you to think about it. Basically, the entire system here can be a huge data flow graph. Different programs have different data flow graphs, and they communicate with each other. Whenever an input comes from outside, it gets into a data flow node, and that gets communicated. So it's a perfectly inherently parallel model. Everything is data flow in that sense, right? And there's no sequentiality here, right? I mean, there's a sequential construct that's happening here. There's an iterative construct, but there's no explicit sequential execution specified by anyone over here. You could make this actually more parallel, but I'm not going to talk about that. That will make it harder to really understand. Okay, so basically, now we have a very interesting ISA level trade-off. What do we expose the programmer to? Do we want a program counter or IP in the ISA? If your answer is yes, then you get control-driven sequential execution, and instruction is executed when the program counter points to it. And program counter automatically changes sequentially, except for control flow instructions. This is a sequential model. If you say no, one model is data-driven parallel execution like this. An instruction is executed when all of its operand values are ready, and that is data flow. There could be other models under data-driven parallel execution, but I will not talk about them. And the trade-offs are actually many, many high-level ones over here. So, for example, which one is easier to program for average programmers? I think many people said von Neumann over here, but yeah, that perhaps depends on the education and exposure also. Which one is easier to compile? I don't know. Which one is better at performance? Extraction of parallelism. This, I think, data flow is a lot easier to extract parallelism from. That's why existing machines actually convert the sequential program into a data flow graph internally. Which one is more complex in terms of hardware? Well, it depends, basically. It depends on how you execute each of these things. So, but in data flow, actually, when you design data flow machine, you don't have a choice. If your instruction-set architecture is inherently this parallel, it becomes very difficult to deal with that parallelism sometimes. In fact, people have built a lot of data flow machines, and they figured out that it's very difficult to deal with the amount of parallelism that's exposed in the programs. Okay, so basically, this is an ISA level trade-off. But now we're going to move into microarchitecture. A similar trade-off, control versus data-driven execution, can be made at the microarchitecture level. Microarchitecture level, invisible to the programmer. Let's take a look at it. So, well, ISA, as we discussed, specifies how the programmer sees the instructions to be executed, right? Microarchitecture, how the underlying implementation actually executes the instructions. Programmer sees a sequential control flow execution order in von Neumann, or a data flow execution order in data flow. But microarchitecture doesn't need to obey that as long as it preserves the programmer's illusion, right? As long as it does what it promises to the programmer, internally it can do a lot of tricks, right? Basically, it can execute instructions in any order as long as the semantics specified by the ISA are obeyed when making the instruction results visible to the software. So what does this mean? Basically, visible to the software, architectural state. If the programmer can inspect the architectural state, that architectural state should be modified only based on what the ISA specifies, the semantics of the instruction. Right? And this is going to be very important in microarchitecture lectures that we're going to see. So a programmer should see the order specified by the ISA and the microarchitectural state, architectural state, memory, registers, program counter, condition codes. They should be updated only in the order and the way that's specified by the ISA. So we'll get back to the von Neumann model. We'll talk about data flow later on in a later lecture. But if you're impatient, you can actually learn more about it. And you can actually watch videos. So let's talk about von Neumann a little bit. We're going to jump into microarchitecture, but we've already kind of been discussing microarchitectures. Right? All major instruction architectures today use this model. But underneath, the execution model of almost all implementations is very different. Basically, microarchitecture doesn't follow the von Neumann model. That's the key takeaway over here. What we do, we pipeline instruction execution. We're going to see that. Basically, multiple instructions can be processed in a pipeline manner. You can do multiple instructions at a time, concurrently. You'll do out-of-order execution, as we will see. Basically, we will execute instructions out of the program order specified by the programmer. We're going to separate instruction and data memories internally. But what happens underneath that is not consistent with the von Neumann model doesn't get exposed to the software. This is all hidden. underneath. And that's the key difference between ISA and microarchitecture. ISA, it's exposed to the programmer. It's all about what the programmer should know about to really run programs and control the system. Whereas microarchitecture and implementation of it, it doesn't get exposed. So basically, let's go back to computer architecture. So computer architecture actually used to be defined based on the ISA definition, but we have an ISA and implementation definition. So it's the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals. So this is more ISA. So here we're talking about both the ISA and the implementation, right? But there's also a traditional ISA-only definition defined by Gene Amdahl, who was a chief microarchitect at IBM. Basically, he defines it beautifully. The term architecture is used here to describe the attributes of a system as seen by the programmer, i.e. the conceptual structure and functional behavior as distinct from the organization of the data flow and controls, the logic design, and the physical implementation. So this is ISA, basically. The first part is ISA. The bottom part is microarchitecture. So let's talk about this a little bit more. I mean, we've already talked about. Basically, we've already said this, right? What is ISA is the agreed upon interface. This is what the software and the compiler assumes and the hardware promises. In other words, what the software writer needs to know to write and debug system or user programs. And software writer is defined broadly. It could be a compiler writer. It could be an assembly language programmer, right? Microarchitecture, on the other hand, is a specific implementation of an ISA. It's not visible to the software. Microprocessor, when people talk about a microprocessor, it's usually a combination of this, basically ISA, microarchitecture, and circuits, just to define the terminology clearly. And sometimes people use architecture, and usually they refer to it as a combination of ISA and microarchitecture in general. So let's take a look at this microarchitecture. How do we implement the ISA? That's what we're going to concern ourselves with the next N lectures. So there could be many implementations of the same ISA. So MIPS, for example, had many implementations. It's a real ISA that we're studying. x86 still has lots of implementation. I didn't update this, so there's another implementation actually that's not here, perhaps. Power, this is the IBM, actually. IBM Motorola developed this ISA, and it used to be used in early Macintoshes, and they have many implementations. ARM clearly has many implementations. Alpha had many implementations. Today, RISC-V is an open source ISA. There's many implementations. So basically, the same ISA can be implemented in many different ways, as we will see. Now, let's talk about this one. What is part of the ISA and what is part of the microarchitecture? Those are these are good exam questions also. I'm curious how ChatGPT would do in these questions, by the way. Actually, we should really input these exam questions to that and see. So the way I like thinking about it is with an analogy with cars. So this is a car, and how many people use cars here or drive cars? How many people don't drive cars? That's good, increasingly more. So basically, there's an interface that's exposed to the user. This is the gas pedal, right? That's the interface for acceleration. Whenever you're using this, you don't really know how the underlying implementation works, right? You don't need to know. You just need to know the interface. Whenever I press this car will accelerate. Whenever I take off my foot or hand, depending on how you drive, or whatever, something, the car is not going to accelerate. Right? And then there's another interface for the other things over there, right? Clearly. So basically, you don't need to know the underlying implementation. Underlying implementation of how that acceleration actually happens is the microarchitecture of the car, right? That's the internals of the engine, internals of the interconnect, and everything that happens over there. It could be electric, it could be gas, it could be a combination, it could be mechanical, whatever, right? All you care about as a user is you press that and the car goes, accelerates. So that's basically it. Implementation can be various as long as it satisfies the specification of the ISA. So for example, add instruction versus an adder implementation. Add instruction is part of the ISA. Adder implementation, the user doesn't care, right? It could be many different kind of adders, and we've seen some of them, right? It could be a bit serial adder, ripple carry adder. We've seen that. I've already flashed a picture of carry located adder. These have different trade-offs microarchitecturally. Some of them are fast, some of them are costly, they have more area. Some of them are extremely energy efficient, some of them are not energy efficient. So underlying in the microarchitecture, there are a lot of trade-offs, but the user doesn't care, right? Unless the user has problems with it, right? The user says, oh, this ad, I'm doing a lot of ads. Why is it taking so slow? Well, maybe the microarchitecture didn't do a good job, right? So whenever you have problems, then you need to maybe care as a user also. That's what happened with machine learning workloads. Right? I'm doing a lot of multiplies and accumulates. Why is this microarchitecture so slow? Right? Then people design microarchitectures that are accelerating machine learning workloads. So x86 ISA has many implementations. Again, I'm not sure if this is up to date. And just because of this reason, because of this interface to the user, microarchitecture usually changes faster than ISA. How many different types of gas pedals have you seen? Or at least the semantic specification of the gas pedals have you seen in your lifetime? Probably one. I mean, they may be embellished in different ways, but they're all obeying the same interface, right? But underlying there could be many, many implementations. So as a result, microarchitectures are very, very different, whereas ISAs stay constant because there is a huge user base, software base. If they change, right? For example, somebody says, I'm going to design a car. It's going to accelerate if I don't push the gas pedal. That's a different ISA, right? Now, that's going to be a huge change for people who are used to the previous ISA, right? You could do it. I mean, why not? So this is why you don't change the ISA very frequently. Okay, I think I've already answered that question. So we're almost at the end. As expected, I didn't get a chance to go to 9B. But ISA actually specifies many, many more things than instructions. It specifies memory. We will see later on interrupt handling, access control, many, many things. Now you can see the number of pages over here, right? 4,800, 4,000. Actually, more recent ones, 5,000 pages. ARM, supposedly a simpler ISA. It has more pages than x86, as you can see. So this is some good bedtime reading for you guys, if you're interested in this stuff. And you'll learn a lot, actually, by reading these manuals. But I'm not going to give you an assignment. So lecture 9C is going to be about assembly programming. We're not going to cover this in lectures, but this will be useful for your labs. It's good for you to know assembly programming clearly in your labs. And it's going to premiere today, and you can watch it. But also it's available from many, many past semesters. Okay, so that's the end of today. I'll see you tomorrow, and tomorrow we go much deeper into microarchitecture. Have a good evening.